The traveling waves with associated powers when scattered out through the ports, the microwave junction can be defined by S parameters. Dear students, in the last class we have discussed S parameters for two-port network and multi-port network. In this session we will discuss what are the properties of S parameters. S parameter is a square matrix which gives all the combinations of power relationships between the various input and output ports of a microwave junction. S parameters do not use open or short circuit conditions to characterize a linear electrical network. Instead, matched loads are used. S parameters change with the measurement frequency, so frequency must be specified for any S parameter measurements stated in addition to the characteristic impedance or system impedance. There are 4 S parameter properties are discussed in this course. Properties of S parameters. Zero diagonal elements for perfect match network. For an ideal n-port network with match termination, SII equal to 0 since there is no reflection from any port. Therefore, under perfect matched conditions, the diagonal elements of S are 0. Symmetry of S for a reciprocal network is a second property. A reciprocal device has the same transmission characteristics in either direction of a pair of ports and is characterized by a symmetric scattering matrix, which results transpose of S is equal to matrix S. So equation 2. We'll prove this in the next slide. Proof for the second property of the S parameters. For a reciprocal network with a assumed normalization, the impedance matrix equation is V equal to Z matrix into current variables, which is equal to Z matrix current can be represented by the variables A and B. Incident variable minus reflected variable, which is equal to sum of the incident wave and reflected wave. We can write above equation can rewrite by multiplying unity matrix to the right hand side term. Now above equation is Z matrix plus unity matrix into B is equal to Z matrix minus unity matrix into A. Equation 3, where U is the unity matrix as I told before. The S matrix equation for the network is, as we know, it's a matrix B is equal to matrix S into matrix A. Comparing equations 3 and 4, we have matrix S is equal to Z plus U inverse and matrix Z minus unity matrix. Equation 5. Now S transpose is equal to Z minus unity matrix and since the Z matrix is symmetrical, transpose of Z matrix minus unity matrix is equal to Z matrix minus unity matrix. Similarly, matrix of Z plus unity matrix transpose is equal to matrix Z minus unity matrix plus unity matrix. Therefore, S transpose is Z minus unity matrix and Z plus unity matrix inverse. Comparing equation 5 and 6, Comparing equation 5 and 6, we can write S transpose is equal to S. That is the 5 equation. Equation 5 is 1 and the same, Z minus U and Z plus U inverse. That's in the fifth slide, fifth equation, previous slide. So thus it is proved that S transpose is matrix of S transpose is equal to matrix of S for a symmetrical junction. Unitary property for a lossless junction. For any lossless network, the sum of the products of each term of any one row or of any column of the S matrix multiplied by its complex conjugate is unity. Proof. For a lossless n-port device, the total power leaving n ports must be equal to the total power input to these ports, so that square of the output variables equal to summation 1 to n square of the input variables, or summation n equal to 1 to n I equal to 1 to n ports can be write by following equation. As we know, B equal to S into A. In this case, for I equal to 1 to n ports. If only ith port is excited and all other ports are matched terminated, then all an equal to 0 except AI except AI, so that summation n equal to 1 to n and an equal to all the ports are 0 except AI. That's why S ni AI square is equal to summation n equal to 1 to n AI square. Equation 2, summation n equal to 1 to n Sni square is equal to 1, because for n equal to 1 to n AI square, and here n equal to 1 to n AI square of the right hand side cancels, so remain terms from the second equation is summation n equal to 1 to n Sni square is equal to 1, which is equal to summation n equal to 1 to n Sni and Sni conjugate value. This is a equation 3, and here we have proved the third property. If all n equal to 0 except ai and ak, then n equal to 1 to n is nk, kth port of the S parameter, and Sni conjugate is equal to 0 only when I is not equal to k. In matrix notation, these relations can be expressed as S conjugate and S matrix, transpose of S matrix is equal to unity matrix. A fourth property is shift property. Complex S parameters of a network are defined with respect to the positions of the port or reference planes. For a two-port network with unprimed reference planes 1 and 2, the S parameters have definite complex values. The reference planes 1 and 2 are shifted outward to 1 dash and 2 dash by electrical phase shifts, then phi 1 is beta 1 L and phi 2 is beta 2 L. It's L1 and L2. The new S matrix for the S dash is then given by this equation. When the two-port network S matrix is S11, S12, S21 and S22, and with the phase shift, when the reference planes 1 and 2 are shifted outward to 1 dash and 2 dash, then the phase shifts are phi 1 and phi 2, then new S matrix is denoted by S dash and is given by this equation.